On this worksheet, we're going to be solving this problem of determining what molarity of potassium acetate is necessary to produce a solution that has a pH of 8. This is a pretty complicated problem. The very first thing that we need to do is figure out what component of the potassium acetate compound is actually creating or causing the solution to have a pH. Like which of these two components is giving rise to the pH. So what we want to do is imagine the dissociation of the potassium acetate, splitting it apart into its cation, which is potassium ion, and its anion, which is the acetate anion CH3COO-. And our goal here is to figure out, of these two, the cation and the anion, which one is contributing to the pH. So which one is neutral? We want to classify them: neutral, acidic, basic, etc. The potassium ion K+, because it's a group 1 ion, it is a neutral cation. All of the cations in group 1 and group 2, they're always neutral. The acetate CH3COO-, this is not one of the list of neutral anions, which means that it is one of our basic anions. Because our cation is neutral, our anion is basic, we know that it's the acetate CH3COO- that's causing this solution to have a pH of 8. So this is the component that we need to pay attention to. We don't really need to pay that much attention to the potassium. I'm going to just kind of set us up to make an ice table, but we're not ready to make the ice table yet. So now that we've identified that the acetate ion is the one that's causing the solution to have a pH of 8, the next thing that we want to do is figure out how the acetate is giving this solution its pH. So we want to write an equation showing that acetate ion acting as a base. That means we want to react the acetate ion with water, and we want this to act as a base, which means it's an H+ acceptor. So we want that acetate ion to take an H+. So there I've given it its extra hydrogen, and also since it's taking an H+, the charge is going to go from a negative charge up to a neutral charge. The acetate is taking the H+ from the water molecule, so that means that the water molecule loses one of its hydrogens, and it also loses a positive charge, which just results in the formation of OH-. And this is the component that is creating the pH of the solution right here. So let's get ourselves set up for another ice table. We know that we want our solution to have a pH of 8, and all of that whole entire pH 8 situation, it is all coming from the amount of hydroxide that we have in this solution once equilibrium has been reached. So this is the number right here, whatever I've got, getting ready to put this number in. This is where we're actually going to be starting our ice tables, and we're going to be working our way backwards up to the beginning. So since we know that we have this solution that we want to have a pH of 8, it's actually going to be more useful for us to think about it in terms of pOH. Because pH and pOH are equal to 14, we know that if we have a pH of 8, that means that solution's pOH is 6. And if we know the pOH of a solution, we can use that to calculate the molarity of the hydroxide ion. The OH- is 10 to the negative pOH, which for us is 10 to the negative 6. And again, this hydroxide concentration, this is what we are ending with when all of this reaction is completely done. So I'm going to fill that in, and I'm going to leave it as the 10 to the 6 form, just to save space a little bit. Okay, so let's keep our eye on the prize and remember what it is that we're trying to do here. We are trying to determine the molarity, the initial molarity up here of this solution. What number do we need to put here that after we do all of our ice table business is going to give us 10 to the negative 6 down here on the bottom. So I'm going to begin by let's call this Y. And I don't want to call it X because we have a purpose for X in our ice tables. It means something. So I'm going to use a different variable. I'm going to call this Y. We're initially starting with some amount of KCH3COO, initially starting with no potassium and no acetate. Because this is an ionic compound and it completely dissociates, we know that all of that potassium acetate is going to dissociate, and it's going to produce potassium ions and acetate ions. And once this is done, we will have no more of the potassium acetate molecule. We will have Y potassium ions and Y acetate ions as well. Now, as I said before, we don't really care that much about the potassium ions. What we really care about are the acetate. Once these acetate ions have been formed, the acetate ions, which we're calling Y, are going to react with water, which we always, don't really worry about in these ice tables. They're going to react with water to form acetic acid and hydroxide ions. So in this second ice table, we're bringing down this Y to represent the amount of acetate. Acetic acid is nowhere in this ice table up here, and same with hydroxide, it's nowhere up here. So that means we're starting with 0 of both of these things. We know that some of this acetate ion is going to react, but because it's in equilibrium, we don't know exactly how much is going to react, so this is where we're going to use our X. Minus X plus X plus X. And at equilibrium, we know that we're going to have Y minus X of this acetate. We're going to have X of the CH3COO minus, and I'm just going to kind of scoot this out of the way. We're also going to have X of the hydroxide ion right here. However, we have already determined that the actual number, the actual amount of the hydroxide ion that we're going to form is 10 to the minus 6. So we know the value of X for this particular problem. We know, based on the pH, we know that X is 10 to the minus 6. And so what we can do is everywhere that we have X in this ice table, we can replace that with 10 to the minus 6. So I'm just going to put it here, 10 to the minus 6. Put it right here, 10 to the minus 6. I'm going to put it over here. Oops. 10 to the minus 6. I'm going to get rid of that X completely. And we're going to put it over here as well. 10 to the minus 6. Our approximation is still valid, so we're still assuming that the 10 to the minus 6 is significantly smaller than Y. So what we need to do is solve for Y, again, because Y is the number that we're trying to come up with. Using the information from this ice table right here, we can write an equilibrium expression. This equilibrium expression is going to be a Kb because we're dealing with a base, and it is going to be our products, which are both 10 to the negative 6, and that's squared because we have 2 of them, over Y, our term for the reactant. So all we have to do is plug in our Kb, and we'll be able to solve for Y. Looking back up at the problem gave us the Ka of acetic acid, and that's actually pretty common in these particular types of problems. You're going to be given essentially the wrong equilibrium constant, so you're going to have to convert this Ka into a Kb to make it appropriate for this problem. The relationship that we're going to use here is Ka times Kb equals Kw. So if we're trying to figure out Kb, the way that we do that is take Kw and divide by Ka. Kw is the constant, 1 times 10 to the minus 14, and our Ka is 1.8 times 10 to the minus 5. So this works out to be 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5 is 5.6 times 10 to the minus 10. So now that we know our Kb, we can plug this in down here. 5.6 times 10 to the negative 10 equals 10 to the negative 6 squared over Y, and let's solve for Y. Math is a little bit trickier here than ones that we've done before, so maybe I'll write the math out on this. We're going to simplify this. We're going to go 5.6 times 10 to the negative 10 times Y equals 10 to the negative 6 squared. And then we'll divide both sides by 5.6 times 10 to the negative 10 to isolate the Y. It's 10 to the negative 6 squared divided by 5.6 times 10 to the negative 10 gives us a value for Y of 0.001 I'm going to go with that, with 2 sig figs. So let's make some sense out of this number. What does this number represent? That 0.0018, that is the molarity of the acetate, CH3COO- that we need. I'm going to change that into scientific notation. This is the concentration of the acetate that we need to produce this solution that has the desired pH. This is also the Y value. This is the ending amount of acetate in this first ice table right here. It's also going to be the value of K, K plus right here. And it's also going to be the value of our starting amount of acetate, potassium acetate, 1.8 times 10 to the minus 3. So the answer to this question, what molarity do we need? 1.8 times 10 to the minus 3 molar.